Okay, so in this video we're going to start section 15.9, which is a change of variables, or as I prefer to call it, U substitution on steroids. Okay, so I've written out here how U substitution works when we have a function of one variable. If I'm integrating from A to B, something that looks like this, which is really just the result of taking the derivative of a function composition so that I would get the chain rule. Okay. Then we can do a U substitution. We would basically be letting U equal G of X, and then U prime would be G prime of X dx. And it's, of course, ideal if we have an exact match for exactly what we would get if we used chain rule. If we don't have an exact match, we can sometimes do a little bit of algebra to manipulate things. Okay. But when we do that, we end up getting to integrate just the outside part here. So just the f prime of u with respect to u. And of course, the limits of integration change. We're going to be integrating from the u value at a to the u value at b. Now, pretty much when we do a u substitution for functions of one variable, it's because we look at the integrand and we say yuck. We don't like the integrand that we're given. We would prefer to have a simpler integrand. We almost never look at it and say, oh man, I've got to integrate from 3 to 4. I'd rather integrate from 0 to 1. We almost never do a u substitution so that we can change the interval over which we're integrating. But it's very important to note that the integrand changes and the interval over which we're integrating changes. Essentially, that makes sense, because if we're thinking of this as a signed area, if we're going to change the height, we better change the base as well. Okay. Now, when we have two variables, if we think about looking at a double integral and saying, yuck, I don't want to do that, I can think of several reasons I might have that response. I might have that response because I don't like the integrand, which is similar to my reaction here, or I might have that response because I don't like the region. Either of those can be a perfectly good motivation for doing a change of variables. I'm going to sort of present it as if we're motivated by not liking the region. And one thing that's important is that while we will be switching from x's and y's to u's and v's, essentially we're going to be going backwards in this picture. Okay. So it's as if we have the following situation. I've got some double integral over R of some function f of xy dA. And I'm just going to indicate with a subscript that that's area in the xy plane, because I'm hoping to change to u and v values. So I always want to indicate what system I'm in. And my R is this blobular region that I don't particularly like. It's going to be very difficult to describe the limits of integration there. So I'm kind of hoping that in the UV plane, there's some nice, lovely region S that I can map via some transformation to R. So I would basically have that T of UV would be x of uv, y of uv. So I would have a function with a two-dimensional input and a two-dimensional output. So both x and y would be functions of both u and v. Okay. I'm hoping I can do that, and I'm hoping that t is going to be a C1 function, which just means that it will have continuous first partials. And I'm also going to want it to be a one-to-one function. Now, one-to-one simply means that I don't have multiple points here mapping to the same point here. Anytime I have a function, a point in the domain is going to map to a unique point in the codomain. But I want this to be one-to-one, so I don't want two different points here mapping to the same value. And if it's one-to-one, that means there's an inverse transformation so that I can go back and forth, and I can go backwards. And that's really what I'm hoping to do. because I'm hoping that I can express this double integral as the double integral over s. Now I'd have to express my height now as a function of u and v, and I'm going to get that by doing a composition. So my height would be f evaluated at t of uv. I take a point uv, I plug it into t, that gives me a point in the xy plane in r, and then I plug that in to get my height. So this height is going to be the same as this height, okay? But then I know I'm going to be integrating this with respect to area in the uv plane. And I have no reason to think that the area of S and the area of R are going to be the same, because for all I know, T is going to stretch or shrink things. Maybe it stretches parts and shrinks other parts. Who knows? It could be kind of crazy. So I'm going to expect there to be some sort of a scaling factor to say that this area is some multiple of this area. And that's not necessarily going to be a constant multiple. It's not necessarily it's always twice as big. It might sometimes be twice as big and sometimes be a third as big. Okay? But I'm expecting there to be some scaling factor here, and that's essentially what we see up here. Remember we said, I'm sorry, I wrote u prime. I meant to write du. du is g prime dx. G prime is my scaling factor. It's not necessarily a constant factor. Maybe sometimes it's 2, so du is twice as big as dx. And other times it's a third, so du is a third as big as dx. But g prime is my scaling factor. So I'm expecting there to be some sort of a scaling factor here if this is going to work. Now notice, we're going from this back to this. We're actually, it looks like making the integrand more complicated. Here, having the composition multiplied by the scaling factor was a lot more complicated than just having the outside function. Well, there are going to be times when this does look more complicated than this, but we're going to be okay with that because the region is that much simpler. There are actually going to be times when, even though the formula for this looks more complicated, in reality this is much simpler, so that we're actually simplifying what the integrand is. But notice that when we do a u sub, the g prime gets absorbed into the du. When we're going to do this change of variables, we're essentially working backwards, and so our dA in the uv plane expands to become this scaling factor times dA in the uv plane. Kind of similar to when we do a trig substitution. If you think about a trig substitution, that's another one of these sort of inverse substitutions where rather than introduce a new variable as a function of the old, we introduce a new variable, and the old variable is a function of that in some way. Okay. And when we do that, if you do a trig substitution, your dx expands into something being multiplied by d theta. So the same thing is going to be going on here. Okay. So what I want to try to do is see if we can't figure out what this scaling factor is going to be. And so in doing that, we're going to go through our usual 4-step process. We're going to chop, and we're going to approximate, and we're going to add, and we're going to take a limit. Okay, it's a long process, so I'm going to start that in the next video.